Hi, thanks for joining in back. So today I plan to discuss on uh, it would be a very quick discussion about decision trees for regression, and I want to basically show how to write a decision tree, a single tree, and train that model from scratch, just using NumPy as I have started doing in this series. So earlier I showed in a blog post and a quick walkthrough of that blog post how to do the how to code linear regression from scratch and train it using backpropagation. Today I want to go through the decision tree algorithm, what it does and how do we build a tree, train a tree and predict using the tree basically. So here's a simple toy data set for regression that you can think about. I'll quickly walk through it first and then we'll jump into the code. So let's say we have a set of three predictor variables: sex, duration, heart rate, and we have to predict dependent variable calories. So depending upon these three features, we have to depend how many calories would have been burnt in that particular workout. So we see that this is the data. Our predictions are to be for the calories. So what decision tree basically does is its intuition is like we have to make decisions for different features at different point of time, so that it can lead us to closer and closer to predicting a correct calories value. So one example we can think of, one simplest way could be, so I just looked at this data and I noticed that whenever the duration is less than 24, so whenever the durations 12, 23 and 15, for these workouts data samples, the calories burnt are relatively lower, whereas if we go in the range above 24, they get of the higher magnitude. So I just said that let's say if duration is less than 24 is a decision the model makes, and if it is yes, then these are the predicted values in the training data: 90, 150 and 100 calories for the three samples that form in this condition, and the other three samples that don't form in the fall in this category in this decision are basically with the calorie values 200, 350 and 230. So once we have a set of values in this, let's say we don't want to further make any more decisions, and at this point we want to predict the value. So at this point the predicted value for the calories would be an average of whatever the data samples we have falling into this leaf right now. So basically wherever a node where you make a decision, take a decision, is called a node or a decision node, and the nodes wherein you predict, finally you are predicting the real value or a categorical value, is called a leaf node. So basically let's say these two are of our lead nodes, we have decided them to be our leaf nodes. So in that case we just take the average of these. So for this leaf, if any data sample comes to fall in this leaf, it would have its calorie value equal to 113.3 calories, which is the average, and if any data sample happens to fall in this category in our test data, it will have a calorie value 260 calories. This is an example, one of the most naive or basic example which you can form out of this data set. Another tree I try to make is we take a decision first, duration is less than 24. Amongst those which are having a workout data samples duration less than 24, we say that if gender is male, is a decision making point for us. If yes, then we have two such data samples, 90 and 150 calories, and we take an average of these to do the prediction at this point. And if gender is not male, then we have only one such data sample, so obviously at this point, if any test data fall under this category, we'll predict 100 as the 100 as the calorie for that workout. Obviously, this is not a very good design choice of bringing to a tree to a depth that it has only one data sample in a leaf node, but we'll look into it later. So how do we control these things? But if duration is not less than 24, that is, it is more than 24, then further we can categorize it into break up into heart rate less than or more than 125. If less than, then we have these two data points, and we will predict the calorie value average of these 215, and if not, then we predict calorie value 350. So once we have such a tree trained on a training data set, we can use test data set to traverse this tree and reach to a leaf node, and using that particular leaf node we predict the calorie value for that workout. That's how a decision tree works. Now again, so decision tree is several things work similarly in the decision tree, which is like overfitting, underfitting, regularization, losses. Backpropagation doesn't work the same way in decision trees, so that's one thing we won't need here. But yeah, losses, overfitting, underfitting, then regularizations, these things will be helpful. Not as much as in the basic naive decision tree, but as we progress along in the direction of random forest gradient boosting decision trees or XGBoost, we'll go through all of those videos, all of those algorithms as well. So those things, regularization kind of things will be helpful. But yeah, so I hope you got a quick idea. Now I'll jump into the code for this. So basically here I have this preliminary code snippets written, wherein I use this data set from the calorie prediction playground competition in Kaggle. I have talked about it in the linear regression video as well. So I'll quickly I'll just import these data. There are three files: train, test, and original. Original obviously is the one which was used to make the synthetic versions of train and test using some models. So we do some preliminary data preprocessing, wherein we map the sex feature into numerical boolean feature, male 0 and female 1. We rename the original gender in this original data frame, and then we concatenate train and original DF to increase our data size. This here basically I am just doing splitting the training data into train, dev, and test, so that we can do our training once we have the model ready. So let's begin by writing a decision tree. So I'll define the class as decision tree. So I'll just first outline the methods that we need for this class. So we'll need to initialize it. Then we'll have a fit method. Then we'll have a predict method. So this is what basically our very overview way what our class would look like. So we'll have to initialize the tree, we'll have to fit the tree with training data, we'll have to predict using the tree. So first of all, let's say to initialize the tree, what are the things do we need? So if we, I'm sorry, I think I might have not switched the screen here. Let me quickly do that. So yeah, basically this is the data. We have loaded the train test data frame. We have concatenated with some pre-processing train and original data frame, and then we have split the new training data into train, test and dev splits. So now I'm starting with the outline of the decision tree. We have initialization, fit and predict methods. Initialization, as you, if you remember from that, basically if you can think of it in a way that what are the things do we need. So what we need is self dot max depth. These are the hyperparameters of a tree, basically, which you will have to tune on the basis of the let's say validation set, or yeah, with your more and more experience. Then one thing you can do is how many minimum samples do you want in a leaf node. So I can say it as min samples split. In a split, how many minimum samples should fall, so that we can avoid one leaf to be having only one data point in the end. That would be too much of overfitting. Then we'll need self dot tree equals to, we can initialize it as none. So once we have fitted it into the training model, we'll see that it will be developed. So self dot so we'll have to take the input of these parameters, max depth, let's say we take it as 5 to start with, min samples split, let's say we say it as 2, 5. So this would initialize our model. Now to fit a model, let's say we pass on y and x and y, right? So to fit a model, basically what we need is to one, we'll have to, okay, let me one call, we'll have to, so basically we'll have to recursively, there should be a recursive method wherein we'll have to call this fit method with x and y of that particular node. Then within that we'll have to do the split based on the decision that we are making. So okay, so let me code it through so that you'll understand. Let's define a recursive method for this. So we'll say that self dot build tree x, y, and I'll say depth equals to 0. So when depth equals to 0, is starting the tree afresh. So basically we are going to return this underscore build tree. We'll take self x, y, depth equals to none. Okay, so I have defined a helper function here which would basically return the nodes of the trees, and we can say that return nodes of trees, which would look something like this. It would have features, it would have threshold, it would have value depending upon if the node is leaf node or not. Then it would have, or let me left tree, right tree, right tree. So to do so, first of all, because this is a recursive method, we need a stopping condition as per the like unset rule of the recursive functions. We need the stopping condition. Then we need to we'll need to find out the find best split feature and its threshold. Then we need to, this would be first, second, third step. What we need to do here is basically, once we have the best split and the feature, split the x and y, and then recursively call build tree. Once you have called everything, you need to return the nodes in dictionary format. Alright, so let's start with the first stopping condition. So if self dot max depth is none, if self dot max depth is none, let's say if depth, the variable that we receive here, is greater than max self dot max depth, or self dot max depth is not none. If depth is greater than max depth, okay, so if the depth that we receive here, alright, if it gets greater than max depth, and if the max depth is not none, both conditions should satisfy, then we would stop it. So that means that we have already reached our maximum depth limit that was given in the initialization of our tree. If this happens, or self dot min max min samples split is not, is just basically, if we say if is not none, and if this is not none, and also number of samples is less than self dot min max split. So basically we need Samples, we need to unpack the dimensions of the x that we get an input here. Number of samples and number of features equals to x dot shape. We have this. So if minimum samples split is not none, which is here, if it is while initialization we store a value to it, and number of samples is less than minimum samples split, means we have not reached a stopping condition, that if we reach minimum samples split, that in a input x there are only sample size of this amount, then we will stop. Or even if this condition doesn't meet, then if length of np dot unique, if unique values in y is 1, if any of these three conditions satisfy, if we have only one unique value to end with, means there are no variation in the values at the end, and still none of these above two conditions are satisfying, we can still stop when this happens. So in this case we will return the mean of all whatever the samples we find in y. And let's, because we are returning this in a way of value, because this is the format that dictionary format of each node that will develop, so we'll add the value key to this part, right? Yeah. Okay, now let's find the best split. So best feature, best threshold equal to, I'll need another helper function, find best split, wherein we'll send x, y, x and y. I think that's it. Best feature, best threshold. Here, okay, let me, once we have best feature and best threshold, let's say we'll come back to this method and we'll define it. If we have found best feature is basically a number of the column, index of the column 0, 1, 2, that way, and best threshold is the value at which we should split it, like less than 20, less than 30, whatever. So if we have found it, we can split the values left indices equals to all rows of x, best feature, we'll take entire all the rows of x with the best feature column. Basically we are indexing that particular column, best feature column, and in that best feature column, if it is less than equal to, if it is less than best threshold, so this will give us the indices of the feature which should go into the left subtree. Similarly, right subtree is if it is greater than, if the values in this column of x basically are greater than best threshold, they will go into the right indices. So we have split the tree. Now we'll have to call the the build tree method itself recursively with these with these arrays or with these indices that should go into the left subtree and the right subtree. So basically we'll say left subtree, right subtree. This is nothing but self dot build tree x left indices, y left indices, and depth is equals to depth plus 1. So whatever depth we got in here, that plus 1, right? So let's say, I think we should say that it to be 0. While calling first time we need not transfer it, and once we are calling these, we'll call it with depth plus 0. So once we have found our indices for the left and right subtree, we index them into x and y and pass them to self.buildTree. So basically once these will recursively go on into calling the left subtree, and then in the end it will start building and returning the values again. So once we have found the left subtree, so basically we want build tree to return a dictionary node, a node of a dictionary with all these values that I spoke about here, right? So we are going to add those into this. Once we have built our left subtree, right subtree with this, we'll return feature, which would be nothing but best feature, threshold, which would be nothing but best threshold, left would be left subtree, right would be right subtree, and value. So value is something which in this case we won't be returning. Value would only be returned in case we are reaching a stopping condition. So only then value would be returned, and in that case we don't need other 4 keys in that particular case, in the leaf node case. Okay, here we can say there can be one more condition depending upon if we have a loss function on which we can put a constraint that if our improvement in the loss again. Okay, so the concepts of gene index, gains, etc., and decision tree that are more suitable for the classification function, I'm not talking about those because here we are focusing on the regression problem. So I'll just go through the loss as an mean squared error loss. So if let's say if our loss improvement, reduction in loss is less than a certain amount which we set as hyperparameter in the beginning, so we can still stop building the tree further down the line. So in that case we can say if best feature is none, we can do return of our same thing. We can return the same thing. So if this method returns none for the best feature depending upon the threshold value, we can do this, but I'm not sure if implementing this right now is a good idea, but okay, let's comment it out for now. We found best feature and best threshold using this function, which we are yet to define. Using those features and threshold, we indexed and done the indexing and calculated the values if it is greater or less than threshold, and then recursively called the build tree function for left and right subtrees. And once we are done, we are returning these values. Alright, so now I think is a good time to go ahead and define find best split method, which would take x and y as inputs. So here what we have to do is we have to first of all let's say number of samples, number of features equals to x dot shape. Now first we will have to, so in this, once we have an x which is, let's say, of the size whatever, so n samples and number of features, so we'll have to iterate through all the features, all the columns in the data, and for all the columns we will have to see what are the unique values in that particular column, or if they are numerical values and they are large in numbers, there are a lot of unique values in hundreds or thousands, then we can find a way of calculating the average of every two consecutive values, and those would be our feature checks. So we'll have to check at each unique values or unique points in that particular feature, what would be our total mean squared error loss for left, including left subtree and right subtree, and the case for which feature and which threshold we'll find the lowest MSE, total MSE basically would be the feature, and the threshold will return here, which would be received at this point, right? So let me go through it first. So for feature in number of features, okay, but initially let's start best MSE. We'll need some variables to store these: best threshold, best feature. So these things we can say as none. Threshold would be a value that we are going to compare. So lowest threshold is what we need, basically, sorry, my bad. Lowest MSE is what we are looking for. So we'll start with the largest value and then we'll keep on comparing at each iteration. Best threshold would be, again we can start with none. So we'll iterate in the range of num features. Let's index into the column all rows of this column. Once we have feature values, now find unique values or build thresholds. Now, so there could be a different, so depending upon what kind of feature it is, if it is categorical, you can, it would be better to go think of it as unique values first. in case of numerical as well, thinking about as unique is okay, but I think if the number of numerical values are very large, it's better if we build a list of thresholds based on the average of each consecutive value. So let's say that we have feature values is a vector of length and number of samples, right? So we take feature values, all the values till -1, we sum it with feature values, all the values from 1, right? And then we take the mean of this. So basically this is a list of feature values from first till second last element, and this another one is the list from second element to the last element. So we take these two lists, we add them, do the element wise addition and take the mean of those. So basically in effect what you have is mean of first and second values, mean of second and third values of that particular feature. So we have mean between each of the two values, right? Before that, I think it would be advisable to have a sort of it. Sorted values equals to np dot sort feature values, and instead we use the sorted values here because it would just be thresholds. This will become a list of thresholds. So we have made a list of thresholds basing on the basis of mean of two variables. So if you remember, in our data we have a sex feature wherein we mapped it into 0 and 1, so it became the Boolean feature, but I think here it should work fine because we already have it in numerical form, and it would become like if gender is less than 0.5 or greater than 0.5, so it would effectively make correct decisions. I think that sounds logical. Next would be, once you have a threshold, iterate on thresholds for threshold in thresholds. Whatever threshold we have for this particular feature, left will find the split the values. We will call it left mask equals to feature values. Because this is a vector, we can index them into less than equal to threshold, right mask equals to feature underscore values greater than threshold. So what will this will give us is a Boolean vector of length feature values, with each element giving us if that element in the feature values was less than or equal to threshold or not, and the right will give us the opposite. So these are the basically Boolean vectors. Now we'll have to, using these, compute MSE total. So we'll have to calculate left mean squared error, right mean squared error, total mean squared error, and to do so we will need to index into the y's basically. So we have y indexed with these Boolean vectors, left mask, which will give us y left and y right simultaneously. So once we have these y left and y rights, we have the elements of y's that will belong to the left subtree and right subtree based on this threshold of this particular feature. Once we have these, we are going to calculate mean squared errors. So mean squared errors is basically nothing but difference between the target, the value of that particular sample subtracted from the value that is predicted for that sample, and it is squared and taken the mean over entire data set. So what is the target, what is the prediction here? Basically prediction is nothing but it is the average of entire piece of y left. So you'll see that it would be mean of squared of something, right? So what is this? The error. Basically the error is nothing but y underscore left minus np dot mean y underscore left. So this is total MSE is nothing but left MSE this would not be the mean squared error, this would be residual sum of squares, sum of squared residuals of left. This would be sum of residual squares right. So we are not doing mean here, let's say we are doing np dot sum. Once we have all the residual sum of squares, it should be SSR left plus SSR right, residuals all sum together divided by number of samples. So this should find us total mean squared error. Once we have the total MSE, now we have to, if this total MSE, if total MSE is less than best MSE, best MSE equals to total MSE, and best threshold equals to this threshold, best feature equals to feature IDX. So these three things we have. Yeah. Once we have all of these, we can just at the end just return best feature, best threshold. Once we have these returned here, we can index them into the X data set with these thresholds and features, to further pass it along to build the left subtree, right subtree, and so on. So at every juncture it will run through n number of samples and the features to find the best split, best feature, best threshold, and basis of that it will build left subtree, right subtree. Each subtree is nothing but a node of these dictionaries, a dictionary with all these values. So this basically here is a loss function that we are evaluating while building the tree. So whichever split, feature and threshold combination gives us the lowest total MSE will go into the that particular would be the choice for the splitting at that particular point. Now I think we are done with the fit function. So let's go ahead and write the predict function. So for predict we'll need x as input, and for x in x we have to calculate self dot tree x. Now let's say we need to traverse a tree for x and pass along as tree. But where is this self dot tree building? So we initialize it as none. So we'll assign it as self dot tree here, and yeah, that's it. Instead of returning anything here, we are going to basically returning the value of this into tree. Once we have the tree, so self dot tree as a node, we need to pass to this traverse. We'll need a traverse tree helper function wherein you pass x and tree, and we are doing a list comprehension of this so that we can convert this into np.array. So what this will do is, for each one sample in x, for one sample it will traverse the tree, and for that particular sample it will return a value, a scalar value, in our case a calorie value, and for each sample it will become a list of calorie values, and that particular thing it is making into an array. So we are returning this, but we need to now define our traverse tree function, which will take in self x and a node, right? If node here is nothing but it would be a dictionary, because each node is a dictionary, small dictionary, right, with all these values. So if value in node is not none, we will directly return node value, right? So basically if we are at the tree node, return the value of the leaf node. If we are at the leaf node, return the value of the leaf. Otherwise, if we are not at a leaf node, we'll have some feature or threshold to split it into, right? Feature equals to feature, threshold equals to node threshold left or we should say if x feature is less than equal to threshold, we'll need to return self dot traverse tree x with node would be nothing but self dot tree dot left, node dot left, sorry, we would have to say node dot left. Else return self dot traverse tree x node dot right, and that would be it would return all of the things for us. Yeah, so it will traverse till we get to the point where node value is not none, and then we'll return it. Yeah, I think it sounds good. A few things we might have to keep track of. Here in fit function, when we call fit, if x is an instance of pd dot data frame, we might have to convert x equals to x dot values. If y is an instance of pd dot series, it is not a list, then y equals to y dot values. This is the first thing we need to think of. And another thing is, if so if the x if we get is if x dot ndim equals to 1, let's say if x is nothing but a single sample, right, we might it would be of the size n number of features, then we might have to convert it into x equals to x dot reshape 1 minus 1. So we need to make it into two-dimensional data basically. So we need to keep it as only one row, and depending upon number of features, it will decide the column itself. Right, so yeah, these two things. Now I think our class is ready basically. Okay, so let's say alright, so let's say we define a model, decision tree model equals to a class of max depth, let's say to start with I'm saying 2 or 3, min samples split is, yeah, let it be 5 because we have 5 in the definition, right? So we have initialized this model. Now let's call fit onto it, and we pass x equals to x underscore train, and instead of, because the data is too large, we will just pass it 1000 values, and y also 1000 values. Anything else? No, that's it. Let's see if that even runs. It has no attribute find best split. Oh, alright. So find build tree. In build tree, oh, okay. Find best split method. I see, we need underscore here. Runtime aminos and counter scalar divide. Okay, so I took a quick pause of the video there and I rectified few errors. Here it shouldn't be node.write, it should be node and index into left, because this is a dictionary. And also there were a few typo errors with the function names, so those have been fixed, and we trained a model with maximum depth 3 for 1000 training sample data. And then once the model is trained, I predicted for test data 10 samples, and using the true values of those test data, I'm just printing them out to see how a prediction is. This is a very simple model trained only on 1000 samples, whereas when we have around 600,000 samples with us, at least for trained data. So for 28 it is predicting 33 to 30, for 39 it is predicting 41, 42, 172 it is predicting 119. So there is quite a bit of difference right now that we can see. Now let's say, let me increase the, let's say 100,000 is the data sample we are taking. Let's say we increase this to 8 and we make minimum samples split to be 5. Now it can take a few seconds. Okay, so now again it took some time. I fitted it for maximum depth 4, minimum sample and a split 5 for 10,000 samples. It took 14 seconds to train to fit the model, and it is now predicting a slightly bit better here. 28 it is predicting 28.65, 42 point something for 39. This sees much better value now. So it is approached to its true value a bit more in a bit more of the training with the larger samples. So yeah, this is what I wanted to show. Now with there could be multiple combinations, and we can introduce early stopping, validation, score, printing, all those things inside this class. But this is a basic structure which we can use for training a tree. I think there could be one exercise to follow up on this is we can use sklearn's decision tree class to develop a class with the same data and same configuration to see how does it work. Let's say dot what is the let me see, what is the sklearn decision tree regression class. Tree dot port decision tree regressor model sklearn decision tree, sklearn decision tree model, decision tree will take in what are the main values we need to take in. Squared error criteria, default is a squared error, okay. Max depth, min splits. Max depth is the feature here as well, will take in as 4 and min split 5. 4 min samples split equals to 5. So let's say this is the model we initialize. Dot fit x underscore train, we are 10,000, y underscore train 10,000. So it took 0 seconds. It's pretty optimized. Now sk, or rather let's say I'll just print the same thing here and we'll change the model. Cool. Alright, so we can see that for 28 this is predicting 31, or maybe let's just, yeah, 28 this is predicting 31, 42, we are quite a bit close here, this pretty close, 184, 77, and so on and so forth. So this might not be a good value to compare the two models. We should print the validation scores or test scores basically for these, maybe whatever it is, whatever evaluation metrics we want to evaluate on. Maybe it is root mean squared error, or root mean squared logarithmic error, whatever the evaluation criteria we have, we can use those to compare. So basically we can add one more function to the class wherein we are calculating the validation scores or the evaluation scores. But yeah, that's it for now. I think I took a lot of time, but hope this is clear, and see you in the next one where I'll be going through the random forest or gradient boost methods. Thank you.